Okay, these are the notes for the last section in Chapter 10. It's on Section 10.6 on exponential growth and exponential decay. Now, we've already talked about growth and decay. We talked about it in the first section, how we could classify a growth problem and how we could classify a decay problem. And to do that, we would look at B. If B is greater than 1, it's growth. If B is between 0 and 1, then it's decay. And that applies to this. In this section, we're going to tie everything we've learned in from Section 10.1, 10.4, and 10.5 using common logs and natural logs, because it'll all come to, you'll need to know all of that in this section. The first thing we're going to look at is exponential growth, and we're going to take it a step further. First thing we're going to do is review some stuff about exponential growth that you should already know. First thing is that if this is standard form, y equals a times b to the x, then b needs to be greater than 1. Second thing is that in general, you start small and it grows quickly. You end up with a larger number really fast. It's the second thing you need to know. And then the third thing is the shape of the graph. And it kind of ties into the start small, grows quickly thing. If we're starting here, it's a smaller number, and then very fast, really rapidly, it ends up getting to be a large number. Now, there's two formulas you can use for exponential growth. They're about the same formula, they're a little different, and you use them in different cases. The first formula here is y equals a times the quantity 1 plus r to the t power. Now the first thing, let's go over the variables. Y is the final amount of whatever you're talking about. That's your ending amount. A is the initial amount. R is the rate at which it's growing, but that rate needs to be as a decimal, not a percent. And that's important. That's a common mistake. And then T is time. Whatever time length they're talking to you about. And you need to watch that because sometimes they'll say it grew in 2 weeks, but your time needs to be in days. So you really need to watch time. Rate and time are the two that people get confused on. And that's the most common spot where people make mistakes. But that's the first formula. This is a general formula. It's the more common of the two. You can use it for a lot of different examples. If they don't tell you which formula to use in the problem, you're probably going to use that one, unless there's little context clues in the problem to help you figure it out. But that's the more general formula. The second formula is y equals a times e to the kt power. Now most of the variables are still the same. Y is the final amount. A is the initial amount. E is not a variable. It's that mathematical constant that we talked about in section 10.5. It's that number that's about 2.78, goes out for several decimal places. Okay? It's that one that naturally occurs. That's E. E is not a variable. T, again, is time. And then K is different. K is a given constant. And they will tell you what K is, or ask you to figure out what K is. And K is different for every problem. You use this formula here more so in science, when they're talking about half-lives or third lives of a specific element. And K is something that is tied to that element. It's a number that goes with a specific element. Or it goes with a specific bacteria, or it goes with a specific population. It depends on the problem. And usually they'll tell you what K is, or they'll ask you to find K. And that's usually your indicator that you'll use this formula. If they say find K, or they give you K, or they give you the formula, the specific formula to use. Those are the three cases usually when you'll use the second one. Otherwise, the first one is going to be a better choice. All right, we've got an example here. It says a certain bacteria grows from 40 to 326 in 120 minutes. Find K for the growth formula y equals a times e to the kt power, where t is in minutes. Okay, so it tells us specifically that we're going to use this formula. So it tells us we're going to use that second one. If it didn't, and it hadn't said find k, then we would be using the other formula. Okay? So you really have to read the problem. You got to read and figure out what it's asking for to figure out which formula you're going to use. All right, now one thing I want to point out is that we know it's a growth it says growth in the problem, but one thing you should be looking at are the numbers. It's growing from 40 to 326. My initial amount is 40 and my final amount is 326. My final amount is larger than my initial amount. That's a clue that it's a growth. Sometimes it won't specifically say that it grows or decays. It goes from one number to another, and you have to realize that your first number is either going to be bigger or smaller than your last number, and that's going to tell you whether it's growth or decay. Okay, so let's figure out what we know. Let's list out the variables. We've already said A is 40 and Y is 326. That's how we know it's a growth problem. We're going to find K, and then T tells us that T is in minutes and that it's 120. Now, had it said hours, we'd have to switch minutes to hours or half hours or whatever it tells us. But here it says it's minutes, so that's good. We don't have to change anything. And we're going to plug in what we know into our formula. Y equals AE to the KT power. So 326 equals 40 times E to the K times 120 exponent to the power. Now, one thing I want to point out is that the KT only goes with the E. It doesn't include the A. The A is separate. And when we look at this problem, this is a problem you guys did something in section 10.5 with. It's one that's got an E. You have to solve for the exponent. So you've done a problem like this before. It's not a new idea. Your goal is to solve for K. To do that, you're going to go through your steps for solving a problem with base E. The first thing you want to do is get E by itself. So we're going to divide both sides by 40. 326 divided by 40 is 8.15 equals E to the K times 120 power. Or 120K, you can write it either way. Now our next step is to get rid of the E, because the exponent up there, we got to bring that down. To do that, you did this in 10.5, you're going to take the natural log of both sides. And what happens is that these are next to each other, they cancel each other out. So you get the natural log of 8.15 equals 120K. Now we're solving for K, we're solving for the variable, so now we're going to divide both sides by 120. And K equals the natural log of 8.15 divided by 120. And we want that as a decimal. Usually we take these out to 4 decimal places unless it tells you otherwise, and you're going to have to figure that out in the problem. For K, in general, every problem you do where you're solving for K, K is to 4 decimal places. Alright, so we're going to put that in the calculator. Now I will warn you, you have to put it in the calculator correctly. And we talked about this a little bit last time. It's really important it gets put in there correctly. If you're going to put it in the calculator, it would be the natural log, it opens parentheses, 8.15, close it, divided by 120. Make sure the parentheses get closed, otherwise your answer is going to be off. And when you do that, your decimal ends up being K equals 0.175 when you round it to 4 decimal places. And there would be the answer to your problem. Now one thing I want to point out is that K is positive. That's your indicator that you did the problem right. If K is positive, that means it's a growth. If for some reason you got K to be negative, then your problem, you don't have done something wrong in the problem, because K has to be positive in order to be a growth. It's positive in your exponent up here, okay? So your answer should have been positive. Okay, there's your example for exponential growth. There are many other types of examples, so don't feel like that is the only one. You have that other formula there also, and you can solve for any of the given variables. You can solve for the final amount, the initial amount, or the rate, or the time, whatever it tells you to. So there's a bunch of different variations here. We're going to move on now. We're going to go to decay. Exponential decay, let's go over some quick facts. We said this earlier, that b is between 0 and 1. They're going to start with a big number, and then it quickly gets smaller, which means the graph would look like this. This is your beginning point, this is your end point. It started out with a large number, and then it fell off really fast. And it falls off and it hits a certain point where it's never going to cross the boundary. And remember, that boundary is your asymptote. Okay? It won't completely disappear. There'll be a point where it may just fall off and you're going to have a constant number. And that happens every once in a while. All right, there are two formulas for for decay. The first one, notice they look almost identical to the other two. First one is y equals a times 1 minus r to the t, and the second one is y equals a times e to the negative kt power. Differences. Here we're subtracting, and the reason that we subtract is because when we subtract that, we will get a number between 0 and 1. If I take my rate away, then I get some decimal between 0 and 1, which is what you want for a decay problem. In the other one, if we add it to it, then we get something larger than 1, which is what we want for a growth. So that's something to watch too. Really pay attention to what's going on in the problem and how all of this stuff comes together. In your other formula, the only difference is that k is negative. Okay, now if they ask you to solve for k in this problem, k is going to end up being positive. The only reason I talked about it in the other one is because you need to make sure that you're getting the right answer. Here they've already put the negative in there. Okay, so it will be in the problem already. And when you get your answer, k won't be negative. It's still going to be positive, but it has the negative in the problem. Okay? Here's our example. It says a furniture store is closing out its business. Each week the owner lowers prices by 25%. After how many weeks will the sale price of a $500 item drop below $100? Well, they tell us everything we need to know in that problem. And notice there's nothing about k, so we're not going to use that second formula. We're going to use y equals a times 1 minus r to the t power. It doesn't say anything about k or anything about a specific element or anything, so we're going to use that first formula. Let's figure out what variables we know. Our final amount has to be 100. Okay, that's where we want to end up. And our initial amount is 500. That's what I was talking about earlier with the 40 to 360. Notice this time it's getting smaller. I started with 500 and it's going to 100. That's a decay problem because it's getting smaller. Our final amount is smaller than what we started with. T is what we're going to be looking for. Okay, we don't know T. It says after how many weeks. And then our rate, it says it's 25%, but we can't leave it at 25%. We need to make it a decimal, which would be 0.25. If you leave it 25, then your b ends up being negative. 1 minus 25 is negative 124, negative 24, which doesn't work. That's not an exponential because b always has to be greater than 1. So really think about what you're doing. All right, we're going to plug in our numbers, plug in our values. Our final amount is 100 equals 500 times 1 minus 0.25 to the t power. We're going to find t. All right, let's get t by itself on one side. And to do that, we're going to divide by 500 first. We are not going to distribute because the quantity has an exponent, and you can't distribute into something with an exponent. So we're going to divide by 500 first. And that's a common mistake. So make sure that you divide right off the bat. 100 divided by 500 is 0.2 equals 1 minus 0.25 is 0.75 to the t power. Now you've done a problem like this. You can't get the same base on both sides. This is something you've done in 10.4. So what we're going to do is we're going to take the common log of both sides, log base 10 to the t. What happens now is that your exponent up here can move out in front. That's the power property. And then we can divide both sides by log 0.75. So we end up getting t equals log 0.2 divided by log 0.75. And that would be our answer. And we have to figure out what that is as a number, and we want to know how many weeks it's going to take for the price to drop below $100. We're going to put it in the calculator. Again, be careful putting it in the calculator. I would actually do it in two parts. For some of you, that's going to be a lot easier. Okay, we've got log 0.2. and that is negative 0.69897. Took it out 5 decimal places. You can take it out 6 just to be safe because you're going to have to round it eventually. And then the second one, the denominator, log 0.75, is negative 0.124939. Okay, and I rounded up that last number. Now you put that in the calculator, negative 0.69897 divided by negative 0.124939, and we get t equals 5.59. Okay, what this means is that it's after week 5 starts. It's gone 5 full weeks, and it's still the price still hasn't dropped below 100. So somewhere in week 5 it drops. That's what the decimal tells us. That means it's going to take 6 full weeks for that price to drop below $100, to go from 500 to below 100. So 6 weeks would be our answer. It doesn't say to round it, so you're going to take it to the full number. And you really need to watch that also, because sometimes it will tell you to round it, sometimes it won't. You really need to think about what your answer is. Okay, so 6 weeks, if you gave me 5.6, I probably wouldn't take off, but I really want to know how many full weeks it's going to take, because that's where the problem is asking how many weeks, not how many weeks and days, how many weeks. So really pay attention to what's going on. A couple things I want to point out real quick before we say we're done with this video is to really watch out for your variables and make sure you're using the right formula. Okay? Go back and use your notes from 10.4 and 10.5 in order to help you figure out the problems, because if you mess the formula or the variables are in the wrong spot, the whole thing is going to be wrong. Probably did the math right, but the whole answer will be wrong. So really watch those as you're working. And then those are your notes for section 10.6 on exponential growth and decay. Bring any questions you have to class next time, and we are done.